Okay, students, today we're going to cover section 4.3. There's two parts to it. So the first part we're going to go over, it's called complements. More specifically, the title of it is called the probability of at least one. Okay, so let's go through the definition. So let me share my screen. And it is on page 159. So the at least one has a meaning. So the meaning of at least one means one or more. The complement of, so we'll talk about the complement in a little bit. So at least one means one or more. So I'll give you an example. So let's say that I invite friends over and for 4th of July, and I tell my friends, I'm going to drink at least one beer. What does that mean? That means I'm going to drink one or more, one or more. One is the smallest. One is the smallest. So that's what at least one means. So visually, let's take a look at it. What does it look like visually? So there's the definition. At least one means one or more. And so on the number line, here's 0, 1, 2, 3, 4, 5, 6, 7, right? So on the number line, one or more, at least one means from 1 above. 1 from 1 and above. That's what the at least one means. It just goes on forever and ever and ever. So from 1 on. So notice that when I highlight that, there's a piece that I did not highlight. This part there is the complement. That region there, that is the complement. So there's a formula for the at least one. So let me write it down. So the probability of at least one means 1 minus the probability of none. I did not shade the none part, this part there, the 1. I made the circle too big. I didn't shade that region. So that's the formula. If I want to figure out the red, all I have to do is just do 1 minus this part right there. That region right there. So that's the formula for at least one. Now, this is the unofficial formula for it. And I'll show you in a minute the actual real formula. So this is kind of like the summarized version of it. So let's do an example of how the procedure works. Okay. So let's suppose for example, you have, the couple that wants to have 3 kids. Couple plans to have 3 children. What are the genders of the 3 children? What are the possible genders of the 3 children? Right, so we can listen, right? Boy, boy, boy. Girl, girl, girl. Boy, girl, boy. Girl, boy, girl. Boy, boy, girl. Girl, girl, boy. Or boy, girl, girl. Or girl, boy, boy. Right? So we have a total of eight outcomes. Total, right? There are 8. And suppose I want to know from our list there, what is the probability that the couple has at least one girl? Well, you can see it easily from our list. We can point them out. At least one girl means that they have one girl or more within the 3, right? So let's highlight the ones that have at least one girl or more. So this one has one girl. This one has at least one girl. This one has at least one girl. This one has at least one girl. That one has at least one girl. That one and that one. Those are the ones that have at least one girl within the set. So if I do my probability, there are 7 out of the 8. 7 out of 8. Right now, if I use my formula, let's do the formula. Probability of at least one girl is equal to 1 minus the probability of no girls. Right? So if you look at your list, from our list here, out of the 8, which ones do not have any girls? Only 1. Right? So if I put it for this part there, 1 out of 8, and I use my famous adding or subtracting fractions, right? I need to have common denominators, so I need to convert 1 with a denominator of 8, so I can express 1 as 8/8 and subtract 1/8, and you get 7/8, which is what we got when we listed all of the outcomes. You can see it easily, but if you don't, you can use this formula. The thing with the formula is that you need to find the total number of outcomes. That's the secret. You don't need to write out all the different possibilities. It's going to take a long time to do it. But if you calculate the total, we can figure out using this formula easily the probability of at least. All right, so let's do another example. We'll make it a little bit more of a challenge, right? So suppose a couple plans to have 8 children, right? 8 children. What is the probability that they have at least one girl? Right, one girl. All right, so we need to figure out the total number of possibilities there are for this couple, all the genders of all the 8 children. Now, you remember back over here, right? We knew that it was 8. How did we know that it was going to end up being 8? Well, there's 3 children, right? 3 children. Each child has how many genders? Well, there's 2. There's 2 genders. 2 for the firstborn. There's 2 genders for the second, and there's 2 genders for the third. If you multiply those 3 numbers, you get 8. Right? Now, we're talking about a couple that's planning to have 8 children, right? So if I list 1, 2, 3, 4, 5, 6, 7, 8. Each child has how many? There's 2 genders for the firstborn, 2 genders for the second, 2 for the third, 2 for the fourth, 2 for the fifth, 2 to the sixth, 2 to the seventh, 2 has 8. and you multiply 2 times 2 times 2 times 2 times 2, all those numbers, you get 256. And you don't have to list them all, but I know two for certain. I know boy, 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 1, 2, 3, 4, 5, 6, 7, 8, and I know 1, 2, 3, 4, 5, 6, 7. I hope I have space. 8. I know those two for certain. I'm not going to list the rest of the 254. It's just too many. I don't have time. I already calculated the total. I want to know the probability of at least one girl. All right. So if I use my formula, 1 minus the probability of no girls, this would equal to 1 minus, all right, well, out of the 256, which ones have no girls at all out of the 256? Well, there's only one. The one that has straight boys. Straight boys. That is 1 out of 256. Right? And so if you calculate it and you do the same thing like we did here, remember we got to convert 1 as a fraction containing a 8 as a denominator. Well, this one, I have to make the 1 into a fraction that has a denominator 256. So that means this has to be 256 over 256. That's 1, right? Minus 1 over 256. We get 255 over 256. Interesting. So I want you to look at this number, and I want you to look at the other number that we did with the 3 kids. What do you notice about the 2 fractions? Oh, look, the numerators are one off than the denominator. Interesting. Interesting. So there's a pattern here. There is a pattern. All right, so now that you know the pattern to it, now I can show you all the main formula for the at least one probability. So here is the official probability of at least one formula. The probability of at least one is equal to 1 minus the probability of none raised to the nth power. Right? So this power here, this power there, that represents the number of trials. You'll have to look for that in the word problem, the number of trials. Right? So I'm going to point out something else too, is that the item that's in here and the item that goes on the right there are going to be complements of each other. So let's say that this says at least one boy. Well, on the formula, it's going to be the opposite. So opposite of boy would be girl. If this is girl, then the opposite would be boy. So these two are going to be complements. Whatever this is, you know the complement's going to be the opposite. If this is good, the other one's bad. If the other one is heads, tails. Success, failure. Failure, success. So they're complements. All right, so let's go to the exercises and let's attempt it. A couple of them. I think there's 2 of them. Not too sure. Let's check it out. So if you go to page, I think it's 166. We already did number 6. We already did number 5. Let's do number 7. All right. Let me read it out. and then we'll do it. All right, so number 7 says, in the United States, true probability of a baby being a boy is 0.512. We thought it was 50%, but it's really 0.0512. So how you're asking, well, how do they know? How do you know it's 50-50? Well, every year they've been taking data every year of the genders of children every year. Some years it's girls, some years it's boys. It alternates sometimes. Sometimes it's overpowered by one gender than the other several years. But they compile all of the data for all the years that they've collected data. Come to find out that on the average, it's 50% boy, 50% girl. But here it says, I guess at that time, back in 2005, when this book was written, they concluded that it was 0.512. All right, so I'm going to write it down. So the probability of a boy is 0.512. Boy is equal to 0.512. Right, and so we're going to have to figure out, we'll have to figure out what the other probability is. If we know boy is 0.512, I need to figure out its complement. So you always want to figure out the complement of whatever item that they're giving you. So we'll figure that out in a little bit, right? But number 7 saying, among the next six randomly selected births in the United States, what's the probability of at least one of them being a girl? All right, so they want you to find the probability of at least one girl. Right, so that's what they're asking for. What's the probability at least one of them is a girl? All right, so I wrote it down. Share my screen. And let's figure it out. So here's my probability that they're asking me, right? So when I write my formula, I gotta do 1 minus the probability. So if this is girl, then the other one has to be boy. Remember, they gotta be opposite. And I gotta raise it to a power. So we need to go back to the problem and figure out what is that number, that little exponent that's gonna go above the parentheses of the boy. So let's go back to the problem. Let's see if you can figure out what is that number. Okay, someone's saying it is 6. You are correct. 6 is the number of trials. So we're gonna raise it to the 6th power. We're gonna raise the probability of boy to the 6th power. Okay, now because it's asking you for boy, we don't have to find the other one, but let's just do it anyways. So we know if boy is 0.512, what's the girl? Well, all you do is subtract to figure out the complement. 0.512, I'm going to subtract, and that's going to give me 0.488. So we need to know the two events, right? Just to be on the safe side, right? So here's the probability that they're asking us. Find the probability of at least one girl. We found it is boy. So now I just plug it in. I know from my chart here that boy is 0.512. I'm going to close the parentheses. I'm going to raise it to the 6th power. Now you're asking me, how do you put that in your calculator? Simple, just the way it looks. So we're going to do 1 minus parenthesis 0.512, close it, and then raise This is the key for the power is going to be this little hat. This little hat button there represents the power. So you press it. Oops. It's supposed to be 6. And I think I have too many parentheses. I need to take one out. Let's see, take that one out. I don't need that one. There we go. There you go. 0.1 minus 0.512, raise it to 6. Hit enter. Round it to 3. Answer 0.982. 0.982. All right. Let's do that. This was number 7 in your book. That was problem number 7. Number, not example, but number 7. All right, I'm gonna skip number 9. We're gonna do number 11. Okay, let's do number 11. And let's see if we can do it. All right, number 11 reads. All right, so at least one defective iPhone. It has been reported that 20% of iPhones manufactured by Foxconn for a product launch did not meet Apple's quality standards. An engineer needs at least one defective iPhone so she can try to identify the problem or problems. If she randomly selects 15 iPhones from a very large batch, what's the probability that she will get at least one that is defective? Okay, so they want us to find the probability of at least one defective. All right, so that tells me I'm going to have to look up, I'm going to have to find the probability of defective in the problem. And so what's the opposite of defective? Effective, I guess. All right, so I guess they're good. I mean, they're I guess they work. Effective means they work. All right, so let's go back and see, what does this 20% represent? I believe the 20% is the defective. So defective is 0.20. I would hope so, right? So 20 is defective, probability defective is 0.20. I wrote 20% as a decimal, so I rewrote it as 0.20. So what does effective mean? If this is 0.2, then that means this is 0.8. Remember, they are complements of each other, right? Or you just did 1 minus 0.20, you get 0.8. All right, so we got the two variables, the defective and the effective, and now I'm going to find the probability of at least one defective. All right, so I'm going to use my formula. So it's 1 minus the probability of, remember it's going to be the opposite, so this should be the effective. And I believe it said 15. 15 represented the number of trials. Let's see, where was this? I thought I saw 15. Yes, there it is. If she randomly selects 15 iPhones from a very large batch, there you go. So that's going to be your N. That is your N. So raised to the 15. And I just plug it in. 1 minus my probability of effective is 0.80. And I'm going to raise it to the 15th power. And I'm just going to calculate it. I'm going to let my calculator do the job. So 1 minus parentheses 0.80 raised to the 15. 0.965. 0.965. can check it to see if it is correct. All right, excellent, excellent. And you guys can do number 9. Let's see if y'all can do number 9 for your homework. Okay, so that's the complement of at least one material. And now we can move on to the next part of it, which is called the conditional probability. Let's take a look at the conditional probability. Okay, so now last part of 4.3 is conditional probability. All right, so just like we had keywords for the addition was or, multiplication was and, this one has its own keyword. So the keyword for conditional is going to be the word given, right? Given. And the formula, let me share that with you. The formula is on page 161. No. Yeah, 161. All right, so there's the definition. So the definition of conditional probability is that it is an event that is a probability obtained with the additional information that some other event has already occurred. And the notation for it is B/, not divide, but it's B/A. We've seen that symbol before. Do you guys remember where we saw that symbol? That symbol came from one of the multiplication rules. Was it with replacement or without? Remember? Yes. It came from the without replacement. All right, so let me give you the formula for it. So the probability of B/A is equal to the probability of A and B divided by probability of B. So there's our formula, right? And just to show you, just as a side note, I'm going to show you where that came from. All right, so I'm going to cover that up real quick. I'm going to show you where it came from. So as you recall from the multiplication rule of without replacement, it was a probability of A and B that was equal to the probability of A times the probability of B minus A. And so how did they get from there to there? Okay, well, we rewrote it. It's backwards. So I'm gonna switch. I'm gonna put this on the left and then put that on the right. Just to make it a little bit more clear so you can see it. So I'm just rewriting it. So I move this over here and that over there. That goes there. Right. And so what they did is they wanted to isolate the P/A by itself. So they did some algebra, right? So they divided both sides by P of A and that's how they ended up getting that formula. They just did a simple movement of a term, and that's how they got to that. But that's irrelevant. You don't need to know that. This is the formula that we're going to use. All right. So there's a way to remember it. All right. So the way I was taught to remember it, we had a name for this. So if you look at the variables, so you have B slash A, right? When you look at the right side of the equals, something happens to these two variables. You see the B and the A? What happens over here? They got swapped, right? They got swapped, and then I wrote the column. Hold on, that should have been an A. Thank you for clarifying that for me. Thank you. That should be an A. So we call it the swap and drop. Swap and drop. We swap them, and then you drop the very first variable down. You just drop it down. So we call it the swap and drop. Should put it over here. Swap and drop. Swap and drop. Okay. Now, when you guys go in, because you're going to get a Punnett square again, right? You'll be working with Punnett squares. So just letting you know that when you do your Punnett square, the value that belongs to the top portion of the formula is going to be a value where they intersect. So the top number will be an intersection. And the bottom is going to be a subtotal. Subtotal. Intersection is the top, bottom is the subtotal. Okay. So I'm going to show you how it works. All right, so let's say, for example, that I want to use the we use the drug one. We'll make it up. Yeah. So let's do an example. So let's suppose that subject got the B in the words subject uses, subject not use. Right? And you have a drug test plus test result minus drug result, right? And we'll put in the numbers. Let's say that's 44. This is 90. This is 6. And that's 860. Right. So just like you did with the addition rule, you have to add the columns and add the rows. So this is 866, 134. This is going to be 50. That's going to be 950. 950. I think it's 950. I'm not too sure. I'm gonna add it up. 90 plus 860 is 950. Yep. Gives me a total of 1,000. There's my grand total, and there's the reds are in subtotals, and then I have the inner values within the box. All right, so let's do 2 examples, right? So let's suppose, based on our table, I want to find the probability of subject uses / positive test result. Okay. All right, so I'm going to use my formula. So as you recall, here you don't do the formula yet. Don't compute it yet. You want to go ahead and start doing your swapping of the variables first. Do that always before you start computing, because if you do the computational first, you're gonna get confused and you're gonna get it wrong. So let's go to the motion, and remember that our formula was to swap and drop, right? So I'm going to swap them. So instead of subject goes first plus second, now I'm gonna do plus first and subject uses, and then I drop the first variable, right? And so there's your formula. Okay. So now you want the numbers. So remember this top number is going to represent a value within the box. This is where they intersect. So I want to know, where does plus and subject uses drugs intersect? And it occurs at 44. There's plus, there's subject. This is the box. So that's 44 divided by, I want to get the subtotal of the plus. This is a column category. So I want to get this number, 134. And you compute it and change it to a decimal, and then remember to round it off 3 places. So that would be 44 divided by 134. That would be 0.328. 0.328. Okay. All right, let's do another one. Now, the formula only works. It only works when you have a row, column, row. It can't be done like the disjoint. These two events cannot be the same category. They can't be subject uses, subject not uses, because it doesn't work. It's got to be from two different categories. So let's do probability of negative given subject not used. Okay, subject not used. All right, so here we go. Just down. And we're going to compute this. All right. Okay. All right. So let's go through the motion. So we're going to do the swap and drop. So I'm going to reverse those. Subject not used and subject not used and negative divided by probability of subject not used. Always the first one. When you do your swap, the first item comes down. Not used. All right, so here we go. So remember the top, I need the value within the box that represents where subject not used and negative. Subject not used, negative. There it is. Bam. 860. So 860 divided by the total number of subjects that did not use. That's a row total. That would be 950. So 860 divided by 950 is 0.905. 0.905. All right, so there's your examples. All right, so now we're going to go ahead and do the ones in the textbook. And the one in the textbook is kind of confusing, but we'll go through it. Okay, so let's go to the book and let's look at number 13 on page 167. So here's the table talking about, they did an experiment and wanted to know, they gave students, they had the they were comparing to see what would students do if they were given a quarters or cash, $8. Okay, and there's the table. Okay, so table. All right, so I'm going to copy it down. So it says, in an experiment to study the effects of using 4 quarters or a dollar bill, college students were given either 4 quarters or a dollar bill, and they could either keep the money or spend it on gum. The results are summarized. So here's your table, right? And so we're going to go ahead and add the columns, add the rows, and then we're going to answer the questions. Now, you guys only have to answer part A and part B. You do not need to answer part C. We're not ready for C. All right, so let me go ahead and add the columns and rows for you. And I'm going to replace purchased gum with spent money because that's what they did. In order for you to purchase the gum, you have to spend the money, right? So there's where the confusion falls. Spent gum is really purchased gum. And you know. All right, so I scratched it out, put spent gum. So I added them, 39. This is 50. Row total is 43, and the other row is 46. Grand total is 89. All right, so here we go. Let's do number 13A and B. All right, so number 13 asks for find the probability of randomly selecting a student who spent the money given. You guys see it? There's the hidden word, the keyword given. That tells you right there. It prompts you to use the condition rule. All right, so given. All right, so I know my probability. So I'm going to write right on the left of given, I'm going to write spent money. So spent money, and then given means a slash. Spent money. There's a slash for given. And then after the word given, I'm going to write student was given 4 quarters. Given 4 quarters. Right? And here's what I have. Having trouble with my mouse. Okay. And so there it is. Spent money given 4 quarters. All right, so I'm going to go through the motion. I'm going to swap them. I'm going to put given 4 quarters and spent money divided by, I'm bringing the first item down, given 4 quarters. And I'm going to go to my table. I want to know where these two variables intersect. Given 4 quarters, and they spent the money. Well, spent money was purchased, so there it is, 27. So 27 is the top number, right? Divided by, I need given 4 quarters. Given 4 quarters is a row. So I'm gonna put that on the bottom, 43. So 27 over 43, get the decimal amount. I get 0.2628. 0.628. There's A. Now let's do part B. So part B asks us to find the probability of randomly selecting a student who kept the money given. All right, so kept money. I gotta write kept money. Kept money slash given. There's the word given. That the student was given 4 quarters. Given 4 quarters. Kept money, given 4 quarters. All right, so I'm going to go through the motion. I'm going to swap. Given 4 quarters. And kept moolah divided by, I'm writing down given 4 quarters. That's the first item, right? So given 4 quarters. All right. And I'm going to go through the motion again. Where does given 4 quarters and kept money intersect? Given 4 quarters, kept money. There it is, 16. Remember, the top is an inner circle. So 6 inner circle square. 16 divided by the total number of given 4 quarters. There it is. That's a row. That's going to be over 43. So 16 over 43 is 0.372. 0.372. All right, so that's 13. Right, so now we can try number 15 using the same box or Punnett square. We're going to do number 15. We'll do part A and B. We don't have to do C. We can skip C. We don't need C. All right, so let's look at number 15. So 15 says, right, find the probability of randomly selecting a student who spent the money. All right. Spent money, given is a line. That student was given 4 quarters. Given, that it sounds familiar. Oh, didn't we do that one already? I think we did this one. Let's see. All right, so wait a minute, 15. Yeah, 15A is the same thing as 13A. Oh, what do you know? It's the same thing. Well, that was easy. It's the same thing. It's going to be, okay, so I didn't have to do much. 2743. Interesting, the author didn't realize that he wrote the same problem. All right, so bam, there you go. There's part A. Same thing. Spent money, given 4 quarters. That was easy. All right, let's see. I wonder if he did B the same. Let's see if he did B. 13B. Let's see that comes out the same. Okay, what would B? So B is find the probability randomly selecting a student who spent the money given, that the student was given $1. Okay, then yeah, it's different. All right, so we got spent money given is the line, given $1 bill. Yeah, that's different than 13B. Okay, so we'll have to do that one for sure. Okay, so I wrote it down. I wrote down my problem. All right, so it was spent money / given $1 bill. All right, so let's go to the motion. Probability of, I'm going to swap them. Given $1 bill and spent money divided by, we'll bring this down, given $1 bill. All right, so the top, remember the top is going to be, what does it intersect? Given a bill, $1 bill, there it is, given $1 bill and spent money. All right, so that has to be 12. So 12 goes in the top, right there. Spent money, right? And then now I want to get the total of the given $1 bill. So $1 bill is a row category, so I'm going to follow it. 46. So it's 12 over 46. 12 over 46 is 0.261. 0.261. Again, you guys can write it as a percentage if you want. You can write 26.1 if you want, or leave it in decimal. It doesn't matter. You make the call.